So I'm going to go ahead and introduce Helga. Helga Alexander is the Calibration Program Manager for International Accreditation Service, also known as IAS. She's responsible for assessments, maintenance, renewals, and other activities related to calibration laboratories pursuing IAS accreditation to the ISO IEC 17025 standard. She is also responsible for providing training to the ISO IEC 17025 standard, measurement uncertainty, and other calibration and accreditation related topics for assessors and laboratories. Helga is also an APAC peer evaluator in the field of calibration and the chair of the APAC Calibration Working Group. In previous positions, Helga was metrology manager for a manufacturer of precision measurement instrumentation, as well as quality systems manager for a research engineering organization. She holds Bachelor's of Science and Master's of Science degrees in physics. Welcome, Helga. Thank you so much for hosting this webinar today.
Thank you very much, Laura, for the nice introduction. And hello, everybody. I understand that we have quite an international audience. So good morning, good evening, wherever you are. And thank you for giving me an hour of your time. So today's topic is measurement uncertainty. And it's quite a challenge to do that in an hour, but I'm hoping that I can give you an overview and at least send you in the right direction and get you started. I'd like to start out by just telling you a little bit about IAS. You probably already know we are a nonprofit accreditation body and have been providing accreditation since 1975. And we have currently more than 20 different accreditation programs, calibration and testing being, two of those, and but measurement uncertainty is certainly applicable to some other accreditation programs as well. We're headquartered in Brea, California, but we're really spread all over the world. I'm coming to you today from sunny Florida. We accredit a wide range of companies and organizations, including governmental entities, businesses, professional associations, etc. And we're globally recognized because of our signatory status with the ILAC, International Laboratory Accreditation Corporation Mutual Recognition Agreement, the ILAC MRA, the IF International Accreditation Forum, multilateral agreement, MLA, and we also just recently became a member of the IAAC, the Inter-American Accreditation Corporation, the regional body, and we've been a long-standing member of APAC, Asia Pacific Accreditation Corporation. So that's just a little bit about IAS. If you want to find out more about us, you can contact me. You can go to our website, and I would like you to do that if you're interested. Today's learning objectives to provide you with an overview of how to approach the evaluation of measurement uncertainty, to provide you with an understanding of the importance of measurement uncertainty for laboratories and for their customers, and summarize the steps in calculating measurement uncertainty according to the GUM, and we'll talk about that in detail in a little while. And since this is just an hour-long webinar, and we usually take at least 2 days to teach this course, the last slide I'm presenting will be a very important one for you because it gives you links to more information, because today we're really only just gonna scratch the surface, and some things I may just have to skip over a little bit. So with that being said, let's jump right in. So we all know this is about measurement uncertainty. So let's define measurement. And according to the VIM, the International Vocabulary of Metrology, measurement is defined as a process of experimentally obtaining one or more quantity values that can reasonably be attributed to a quantity. So measurement, by definition, is an experimental exercise of collecting data about something. And as engineers and scientists, we're engaged in measurements every day, regardless of what our disciplines are. And there is, a whole discipline called metrology, which is dedicated to the science and art of measurement, and certainly very much deals with measurement uncertainty as a result as well. And the global economy is very much dependent on good measurements and use of universally acceptable and correct measurement practices. So that's about the measurement. Now the definition of measurement uncertainty, according to Wim again, is a non-negative parameter characterizing the dispersion of the quantity values being attributed to the measurand, or the quantity intended to be measured, and based on the information used. So it really gives us more insight about the measurement, the measurement result itself. So every measurement, has an uncertainty associated with it. There is no way in experimental measurement that you can, get be absolutely, by definition, you cannot, you cannot be absolutely sure that you are arriving at the true value. But we can strive and to reduce measurement uncertainty, but we can never completely eliminate it. So that's something to keep in mind. But certainly, if we want to make good measurements, we have to try and first of all identify the contributors to measurement uncertainty, and then try and eliminate them or mitigate them as much as possible. And such, the contributors could be, coming from the measurement system itself, environmental conditions, the process used, the kind of procedure that you may have set up to perform a measurement, the skill and experience of the operator, and really random contributors where the sources are unknown to us, will contribute to the scatter that we see in any time we make repeated measurements. So why is there such a big fuss about measurement uncertainty? We know it's a requirement of the ISO, IEC 17025 standard, but even if you're not an accredited laboratory, measurement uncertainty is important because a measurement result is really incomplete without an uncertainty statement. You do not have complete knowledge, about your result. So an uncertainty statement, gives you more information, not just the measurement result. A measurement uncertainty gives you an indication of the quality of the measurement, and as such, it instills confidence in the measurement result, and it ensures transparency. And really, if you want to compare measurements, measurement results from one lab to another, then it's really meaningless to make such comparisons without measurement uncertainty. I'll show you a slide in just a moment that will illustrate that. And then we also need measurement. The subsequent use of measurement results may be inappropriate without knowledge of measurement uncertainty. The end user sees the result and may draw certain conclusions, not knowing there's a huge uncertainty associated with that they should take into account when making whatever decision they're making. Conformity statements are one of those decisions that are frequently made based on measurement results. And these conformity statements, when we say something passes or fails, so it's acceptable or not acceptable, something meets a certain specification or does not meet it, those kind of statements could be unreliable, incorrect, without knowledge of the associated measurement uncertainty of the measurement result. And lastly, when you if you need metrological traceability um, of your results, you can't have metrological traceability without the measurement uncertainty, because there's a whole hierarchy of results, metrological traceability hierarchy of measurements, all the way tracing all the way back to the International System of Units. And the measurement uncertainty associated with each step of the hierarchy has to be taken into account in the lower steps. So it's absolutely critical to have measurement uncertainty if you want metrological traceability. And lastly, and that is really also very, very important for testing labs and calibration labs themselves, is that it adds knowledge to the measurement process that you've set up, and it may help you improve your system. So if you're getting a lot of scattered results, look at the contributors to the measurement uncertainty and see how you might potentially reduce the uncertainty and reduce the scatter in your results as a consequence. So just to get back, is which measurement provides us with more confidence? Looking at we have here two measurements, two results. The round dot represents a result. We have here a lower specification limit. So let's say we want to figure out whether this result is inside that specification or not. And we have two labs maybe giving you two different results. The one on the left here has a very large measurement uncertainty, but it's inside. It's still, even with the measurement uncertainty bars here, it's still inside the specifications. The one on the right is closer to the specifications, but it has much smaller measurement uncertainty. So assuming that the measurement uncertainties are evaluated correctly and have taken all the significant um, factors into account, we kind of can decide, well, which one might be a better measurement, and we can decide that better if we know the measurement uncertainty around it. So this is really an illustration of how your result is really incomplete if you don't know the measurement uncertainty that's associated with it. So let's just quickly visit the ISO IEC 17025 standard and its requirements to measurement uncertainty, because I suspect that's why most of you are interested, because you are an accredited lab or you want to become an accredited lab. So the standard has three clauses. The first one that deal with measurement uncertainty directly. The first one is 7.61, which applies to both testing and calibration laboratories. And it says here quite clearly that the laboratories shall identify the contributions to measurement uncertainty. And when evaluating measurement uncertainty, all contributions that are of significance, including those arising from sampling, if you do sampling, shall be taken into account using appropriate methods of analysis. And we'll get back to that in just a moment. A laboratory performing calibration, so all you calibration laboratories out there, including of its own equipment, so testing laboratories who calibrate their own equipment fall under 762 as well. You shall evaluate the measurement uncertainty for all calibrations. So there is no way around it. There is no out. You have to, if you calibrate, if you perform a calibration, you have to evaluate the measurement uncertainty. In clause 763, a laboratory performing testing shall evaluate measurement uncertainty. Where the test method precludes rigorous evaluation of measurement uncertainty, estimates shall be made based on the understanding of the theoretical principles of practical experience of the performance of the method. Now, you see here in clause 7.63 that applies to testing laboratories. it's a little bit more gray than for calibration laboratories. Calibration laboratories, measurement uncertainty is an absolute requirement if you want to claim that you're following the ISO IEC 17025 standard. Testing laboratories, it can be it's a little bit more open for discussion, but we will not, we can't really get into that in this meeting. And for those testing labs accredited with IAS, we have guidance documents that kind of tell you our policies on measurement uncertainty and traceability. So let's back to appropriate method of analysis. That's what the standard says. So in note 3 of the standard, it references three items: the ISO IC Guide 98-3, which is commonly known as the GUM, or the guidance to the evaluation of uncertainty in of measurement. ISO 21748, which is another ISO standard that has more of a top-down approach um, to measurement uncertainty, and the ISO 5725 series. So at the end of the of this presentation, I'll give you giving you links to the GUM and to a lot of guidance documents that interpret the GUM, and basically some of them are specific to a particular industry. So you may want to take a look at that rather than trying to digest the GUM, which is an excellent reference document. But if you want to learn measurement uncertainty, if you're a beginner to measurement uncertainty, it may not be the ideal document to start with. You might be better off starting with one of the guidance documents. So in this presentation, we don't have time to focus on any of number 2 and number 3. We basically concentrate on the GUM because for accredited calibration laboratories, we, in addition to ISO IEC 17025, we also have to abide, laboratories also have to abide by the policies of ILAC, and one of the relevant policies is ILAC P14, and in that document it actually states that the measurement uncertainties for calibration laboratories should be computed in accordance with the GUM. So that's what we're concentrating on here. So back to why we need uncertainty statements. So as I said earlier, an uncertain we need uncertainty to have a complete understanding of our measurement result. However, if everybody computes the uncertainty according to their own little rules and makes up the rules as they go along, and there's everybody does it differently, then there is not really it's really not very useful, because you still cannot compare one result to another if you don't know how the uncertainty was really computed and arrived at. And that was realized back in the late 70s, that this was a real problem. And hence the GUM, or the guide, was first published in 1993 by ISO, and is now published under the JCGM, the Joint Committee for Guides in Metrology, and its member organizations. So it's made available for free if you go to the BIPM website, and I think I have a link to all this on the last slide. So so the GUM is available for free. You don't have to pay $160 or whatever for it, and you can just download it. And various portions of additional information to the basic GUM document are available on these websites as well. So the GUM really helps us to ensure that uncertainty statements from different labs, trace back to the same methodology that give us meaning. And so, there is a lot of still, even with the GUM methodology, there's a lot of arguments and different opinions as to how to compute the uncertainty and how to do it. But at least now the GUM provides us with the guidelines that really lets us start comparing and start having some confidence in the uncertainties. If we compare one measurement result with a given uncertainty to measurement result with another uncertainty, at least we can, if they're from accredited laboratories, we can have confidence that the same methodology was applied. So the GUM is applicable to all kinds of measurements, physical and chemical. It's derivable from a mathematical expression of a measurement. And the uncertainty derived for one specific measurement situation can be used as an uncertainty component for another different uncertainty budget. So sometimes there are multiple nested steps involved to get to your final uncertainty. And really the most important thing is that the international measurement community has agreed to widely accept this methodology for comparison purposes. Um, so so it really provides an internationally accepted practical method for treating non-statistical uncertainties as if they were statistical uncertainties. And we'll get into that in a little moment, a little bit more. But like I said, the GUM, there's more than one way of doing measurement uncertainties. And the GUM is basically a convention that was adopted so we can compare our uncertainties and our measurement results. So I was told not to put any math in it, into this. I don't really know how to do measurement uncertainty without math, but I try and make it as simple as possible. So don't panic. So the first step, I'm going to go through 10 steps and I'll be going through one example step by step. So the first step is to define the quantity that is being measured in terms of your measurement process. Like define what kind of result, measurement result are you going to have, and what are what are the inputs to that result. So if y is your is the measurand or the final result, so that is the value that you want to quantify. And then you may, in terms of setting up an experiment and performing the measurement, you have these certain input quantities that are then combined to give you your output quantity, and it'll make it a little bit clearer. So the example that we're going to use today, is that of measuring the output of a current source very precisely with a precision resistor and a voltmeter. And we're going to be using Ohm's law to determine the current by measuring the voltage drop across a precision resistor. So that, it makes it a little bit more less abstract than what is up here, but it's really just supposed to say that sometimes we can't measure the quantity directly. Sometimes we measure other quantities that lead us to our measurement result. So the step 2 then is to determine your measurement equation. And so the GUM methodology talks about a measurement equation where you really represent your setup and your process in mathematical terms. So in our example, we said we're using Ohm's law to give us a current. So according to Ohm's law, the current I is voltage divided by resistance. So we're measuring the voltage drop, and we're we're using a precision resistor that we with a known value to then work out what our current is. So this whole thing is our measurement equation. Um, so and then what you have to remember that each one of these input quantities, in this case resistance and voltage, have an uncertainty associated with it. And so, you know, earlier all these contributors x1, x2, x1, you know, will have their individual uncertainties that will then have to be combined to get your the final uncertainty of your result. And so that's what I'm going to take you through step by step. That's really all we have time for. So step 3, you calculate your measurement result from your input quantities. So let's assume we've made the measurements. We measured, you know, and I just basically, these are just example numbers. So let's say we measured a voltage drop of 9.009 volt. And let's assume that the precision resistor that we used in our circuit to measure the you know, across through which we run the current and then measure the voltage drop. And I should have put a diagram here, but I forgot. So the precision resistor we know has a value of 10.005 ohms, and we got that from the last calibration certificate. So if we feed that into our measurement equation, we get, you know, I is equal to V over R. And you know, we do the math, we crunch the numbers, and we get a result, a measurement result of 0.89964 amps. So that is our measurement result here. So so if we if we stop right here and say, well, we've got the result, yeah, I can move on. We really don't know very much about the reliability or the quality of this result. So the next step is now to determine what kind of uncertainty is associated with this result, you know, given in amps here. All right, so first we have to figure out what kind of contributors could contribute to the uncertainties for each, you know, for each input. So one of them might be there might be repeatability of measurement, the uncertainty associated with precision resistor. We know there's always a calibration uncertainty, the time elapsed since the last calibration, drift between calibrations, ambient temperature, uncertainty associated with the voltmeter, the ambient temperature effect on measurement devices, the resolution of the voltmeter. This is just to mention a few. Now, the GUM and ISO IEC 17025 requires you to take the significant ones into account. But very often when you don't really have much experience with a process and with a setup, you don't really know what's significant and what's not. So it's best to have more, and then, you know, at least in the beginning, see whether you can you can figure out what the individual uncertainty contributions are, and then if they're negligible compared to the rest of them, then you can drop them, you know, going forward. The other thing that I mentioned here is the GUM really has just two types of uncertainty contributors. It puts it in two categories. Type A is anything that you obtained via statistical methods. So that's usually any kind of repeated measurements that are statistically evaluated. Those are type A contributions. The type B contributions are just everything else, you know, so things that you looked up in a calibration certificate, that you got out of the book, you know, that you got from experience, etc. All these are type B contributors. Now, so going, you know, through this, now let's go back to our example and see whether we can assign some contributors to this example. So let's start with our type A, where we obtain an uncertainty via statistical methods, meaning that we're taking multiple measurements. Let's say in this case, let's say we take 30 measurements, um, and uh, that value that I used in the earlier calculation was the mean or the average of those 30 measurements. So that value that I used in order to get our current measurement result for the current, um, that was an average value of 30 measurements. Um, so then we use the standard deviation of the sample of 30 measurement, and here is the equation of the standard deviation. We use the something it's called like the experimental standard deviation, or the sample standard deviation. If you use Excel, I believe it's called the sample standard deviation, rather than the whole population, because um, we really, I mean, if we really wanted to find the really true value of the voltage here, we would have to take an indefinite number of measurements, and of course nobody once has time to do that. So even 30 is pretty much a stretch, but let's say for the sake of arguments, this was a result of 30 measurements. The standard deviation is based on that sample of 30. And if we crunch the numbers here of standard deviation, we come up with 350 microvolts. So because we used an average here rather than just a one-shot measurement or any of these, X3, X30, or any of these individual numbers, the standard deviation itself, the 350 microvolt, is really associated with assigned to each individual point that you have here. However, if you have multiple points and you're using these multiple points to average them, and then to get your result, this result here, the average, is characterized by the standard deviation of the mean. And for that, we can use the standard deviation, that 350 microvolts that we have, and we can divide them by the square root of the number of measurements we took. In this case, it would be square root of 30. And I hope I didn't make a mistake in the math. That should come out with 60 microvolts. But again, so if you only make 10 measurements, then you would divide by a square root of 10. If you make 50, it would be square root of 50, etc. And you can only do that if you're using the average of the reading as your result. If you use a one-shot measurement, and in your actual experiment, and this standard deviation here was based on a study that you have done before, then you would just use a standard deviation. You would not use a standard deviation of the mean. So yes.
We've got a couple of questions that came through, so
Okay.
I thought this might be a good time to pause and ask those.
All right.
This first one says, does the GUM define significance as relative to the highest MU contributors, i.e., one contributor may be deemed insignificant if 2 orders of magnitude less than the highest contributor?
There is no kind of set rule really on what's significant, what's not. Really, when I do an uncertainty budget and I start with all these and I see something is tiny, and even if even if it was a lot larger, it would still not make a dent into the final number. Then I would say it is insignificant. However, you have to be careful. Some people say, well, a rule of thumb, if it's less than 5% of the total, it's insignificant. But what if you have 10 of these 5%? Then all of a sudden, they can all add up. So you have to be careful, and there is no, at least I know that some accreditation bodies have made rules. We don't. It really depends on the situation. Um, when I'm out there assessing, and someone says, well, it's negligible, that would say, well, did you evaluate that and show me, that this contribution is really negligible, and should be able, later on, I'll show you an uncertainty budget. So when everything, is, if you do an uncertainty budget on an Excel spreadsheet, you can vary, that and see if that was zero, would it make any difference to the final number? So that's really all does that answer your question?
I'll let him respond and tell us
Yeah.
whether or not it does.
Yeah. Yeah.
I've got
And and
one.
and you can, all of you, you can feel free to contact me by email. I put the email up front, so that I'll be happy to respond and discuss it in more detail with you.
I will be
Is
happy to put Helga's email in the chat box in just a moment. I have one more question here.
Okay.
In ILAC P14, what's the reason behind expressing measurement uncertainty to two significant figures?
Um, well, I think what we all have to keep in mind, that even though we have a methodology and everything, we're still talking about um, estimates of uncertainty. And is it, when you look at the budget, and quite a bit is guessing, and your best estimate, um, to really then to go out and do more than two significant figures is kind of, doesn't really make much sense. So that's the answer that I've always assumed, because when you look at what goes into the final uncertainty, and how much you know estimation is involved in that, does it really make sense to squibble about going out to 5 decimal points? I was not involved earlier as to what the other reason might be for that, but it, to me, it never made sense to put an uncertainty out to all these um, digits, when you know how that it really is just an estimate.
I've got one more that came through. How many tests need to be done to do the evaluation?
You mean how many repetitions do you need? Well, it you can't get a standard deviation on anything less than 3, but later on in the presentation, maybe we can hold this question for, because the number of measurements you take really play a role later on into you know what kind of coverage factor you have to use in order to get to a certain level of confidence, and we'll get to that hopefully in a little while.
All right. We've got about 20 minutes left, so if you guys have more
Okay,
questions, just go ahead and type
yeah,
them in the box.
all right. So we kind of came up with we're using the standard deviation of the mean for our type A. So now we have type B contributors, and don't worry, some of the other steps are going a lot faster, but this is really very critical, that we've identified a bunch of things that we think are key contributors, and I want to show you how to use them. So let's assume that resistor, that precision resistor, is freshly calibrated, and the value provided in the calibration certificate is still pretty much that. We know resistors drift, but we have confidence that this is a value that we can still use. And on that calibration certificate, there was an uncertainty, a calibration uncertainty given. So this value, let's say, was given from the with an uncertainty of 0.001 ohm or 1 milliohm, and they also gave a K factor of 2 and a 95% to get to a 95% coverage probability. And again, ILAC P14, the policy that applies to calibration laboratories, which is the ILAC policy on measurement uncertainty, tells us that measurement uncertainty should be reported, and the GUM does too. At 90, the GUM says 95% or above. ILAC P14 says 95%, and this is a coverage factor K equal to that we will explain in a few more slides. So let's further assume that the temperature in the lab is the same as the resistor's calibration temperature, and therefore there's no additional uncertainty contribution or correction due to the temperature, because any of you who know about precision resistors know that the temperature, the environmental temperature is important, and this value here that's given on the calibration certificate usually has a temperature, it was taken at a particular temperature, and if you use that resistor at a completely different temperature, then there's an additional uncertainty, or you have to um, uh, correct for that difference in temperature. So we have the contribution from resistor. Now we get the contribution from the voltmeter, and we have three from that, because we have, again, one from the calibration certificate, we have the manufacturer specification, and the resolution. And let me explain that. The calibration uncertainty from the certificate is similar as it was before. It says 0.58 millivolt at K equal to 95%. The manufacturer's accuracy spec in this particular case, we're using that because we know electrical instruments will drift from one calibration to the next, and regardless of actually whether you're using them or not. And so we kind of want to, we don't know exactly what this drift is at 9 volts. So we're assuming the worst case drift scenario since the last calibration, because if we always keep we send our equipment out to be calibrated, and it's calibrated to the manufacturer's spec, which we assume it is in this particular case, then we can use that as a worst case drift scenario. And here the manufacturer spec is 0.015% of reading plus 1.5 millivolt of the flow spec, and that will give you roughly about 2.9 millivolt. So that's what we get from there. So then the resolution of the voltmeter comes into play as well. Let's say the resolution, we're using the 20 volt range, and the resolution is 100 microvolt or 0.001 volt. But we know this is a digital meter, so if the true reading, so the uncertainty provided by the resolution is not really this full value, it's only half of it, because when let's say this is the 0.001 volt is what your meter shows, and the actual value here is 0.0014. So assuming that the analog to digital converter would do normal rounding, this would round down to 0.001, and if it was higher, if it was 0.0016, then it would round up to 0.002. So that means we're never really off by more than 0.0005, by half of this value. So keep that in mind. We'll work on this a little bit more in a moment. So we have like the raw input of uncertainties right now to put into our uncertainty equation. So now we have to determine the standard uncertainty for each contributor, and the standard uncertainty is defined as a measurement uncertainty expressed as a standard deviation, and that's again from the Vim. Now, that's easy to do with our type A uncertainty because we just, use statistical methods. We computed the type A uncertainty by determining the standard deviation. But what about all these type Bs? How do you determine a standard deviation from the resolution of an instrument? Or how do you, get a standard deviation out of a book, that out of for a value that you've taken out of a book or out of a spec. So here is where this is one important thing that the GUM did for us. It it basically gives us a practical method for treating um, the non-statistical uncertainties, these type B uncertainties, as if they were statistical uncertainties type A. So that we can combine them in the end, because otherwise we would be combining apples and oranges, and that just wouldn't work. So how do we do that? So the GUM gives us a method for treating type A as if they were statistical data with a standard deviation. And we call, instead of, for type B, and that's why when we combine type A and type B, we're talking about a standard uncertainty. And for type B, in order to do that, we assign a probability distribution function to the type B uncertainties. And again, we don't have much time to get into that, but the probability distribution functions were developed for common non-statistical type B uncertainties, and the formula can be derived to calculate the associated standard uncertainties. So basically, you assign this distribution that is, most likely to fit your uncertainty, and I'll talk about that in one of them in a little bit. But if you need to know more about which statistical which probability distribution function to use, we don't have time to get into that right now. But if you go to the end and look at the bibliography I gave you, you can do some further reading. So let's look at what we have right here and what we've assigned here. So the repeatability, we know that is assumed to be a Gaussian or a normal distribution, and we've already we arrived at that 60 microvolt by taking the standard deviation. So we don't have to do anything else to this one. We already have the standard deviation is equal to the standard, the standard uncertainty is equal to the standard deviation of the type A. And in this particular case, we're using the standard deviation of the mean. So the next contributor, the 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 next two contributors are from the calibration certificates, and again, these are normal distributions because that CalLab already did what we're doing right now, is by going through all these steps and turning all these individual contributors to into a standard uncertainty, which is the equivalent, of the standard deviation for a normal distribution. And we could go into the central limit theory. We don't have time for that right now, but the final result, of this GUM methodology will give you the equivalent of a normal distribution. And then we have, here's one that, two that are different. We have the voltmeter, and we decided we're going to use the specs as a worst case drift between calibrations. So so we need to divide, so we assign a rectangular distribution, and the reason we do that is because we know nothing about how they came up with these specs or what that is. It's just a number. So we don't know, if you look at this rectangle here, and the vertical portion is the probability of where where a value might fall on this. We don't know anything. It could be, all we know, it's somewhere in between these outer limits. So the probability that they fall, within the extreme portions of these limits, um, we, we just assume the worst case and think that it's equal. And for that, then to make a rectangle distribution equivalent to a normal to a standard deviation of a normal distribution, we divide by a square root of 3. And I'm sorry, we don't have time to derive that right now, but take my word for it. And you can look it up in the GUM and the other guides, that go into this a little bit deeper. So we take this value, we divide it by a square root of 3, and we come up with this value. Then we have the voltmeter resolution. We already divided by 2 to get that half value, 50 microvolt. And again, we have no idea whether it could be anywhere between these limits, so therefore we assume a rectangular distribution, divide by a square root of 3 to get to our standard deviation, and the equivalent of the standard deviation, which is our standard uncertainty. So the next
Helga,
step, yeah.
we've got about 7 minutes left, and I've had some more questions come through. Did you want to take those now?
I think if you cut me off in 7 minutes, I think I have to push on. Let's keep the questions to the end if someone wants to stay on a little bit longer, and I'll take them. I'll take them by email. How about
Right.
that?
And I'll post
Okay.
Helga's email in the chat
Yeah.
box again for you
So,
guys. So just keep asking your questions
yeah.
if you have
So,
them.
sorry about that. When I did the dry run, I guess I didn't make it in time, but determine in step 7 is you need to the GUM methodology assumes when we combine them the way I'm going to show you they're combined, that there is no a correlation between the individual and certainly contributors. If there is, then we need to do something slightly different. But let's assume for the sake of this example that there isn't. But if you look back at this, we still have these different units. We have ohms, we have millivolts, we have volts, and of course the volts and microvolts and things can all easily be, changed into the same unit. But how about ohms? How do we combine, ohms with voltage, and then we're not really interested. We don't want the uncertainty in ohms. We don't want it in volts. We want the uncertainty of our measurement result in amps, because that's what the measurement result we get. So for that, unfortunately, we have to use something called sensitivity coefficients to determine how much the voltage and the resistant uncertainties contribute to the final result. So sensitivity coefficients describe how an output estimate, in this particular case, the amps, the current varies, with the changes in the input. So how does the current and affect the uncertainty of the voltage affect the uncertainty of the current? How does the uncertainty of the resistor affect the uncertainty of the current? And the way to do that is to use sensitivity coefficients, which can be determined experimentally or mathematically. And again, I have to refer you to further reading, and there's some very good examples or in the literature, and we also go into more detail in our 2-day course on that. And the determination of sensitivity coefficients must take place at or very close to the input quantity values. And, mathematically, they are partial derivatives, but so really you have a mathematical way of determining them, and you have a you have you can also do experiments to determine them. And when I used to be metrology manager, uh, my technicians very often set up an experiment to challenge my math, and fortunately it always agreed. So let me go back to this uncertainty budget that we had earlier, and now you see here the middle one, we have the standard uncertainty units of the contributors, and I also converted it to a percentage or to relative um, uh, relative value of the overall, you know, input that, of the overall, the voltage contribution or current resistance contribution. But over here, I computed the sensitivity coefficient by taking a partial derivative, and then we multiply a sensitivity coefficient by, the standard uncertainty in units of the contributor up here, and that, if you have voltage divided by ohms here, that gives you amp, by definition, of the International System of Units. So this is the value that I get in, this is the standard uncertainty here that we get in amps. And this is going all the way down here. So now we have all the standard uncertainties in the same units. So now we compute the combined standard uncertainty. And that is done assuming that there's no correlation between the contributors. We use a root sum square method to combine them. If they were all correlated, we would just do a straightforward addition and come up with a much larger uncertainty. If we assume the positive correlation. But in this case, we're assuming they're not correlated, which I think is justified with that setup. And so if I do the root sum square of all these inputs that I gave you, I come up with 0.173 milliamps, roughly 173 microamps. And I just ran, a test, so I told you all about these sensitivity coefficients, but you could also root sum square the percentages that I've computed, and I would come up with an uncertainty expressed as a percentage as 0.002 roughly percent. And then, as a test of these two different methods, I did the math this morning, and if you go back and convert that percentage to amps, you come up with that very same result. But I need to warn you that this method of neglecting sensitivity coefficients and using relative values instead will only work if your measurement equation is a product or a quotient. As soon as you have summation in there, it's not gonna work anymore. So you have to go the sensitivity coefficient route. So that's now we combined everything, and there's one last step, and that's to expand the combined uncertainty to achieve a confidence level of approximately 95%. That is what kind of was agreed on in the industry, so in this particular case, since all uncertainties are type B or type A with a sufficient number of degrees of freedom, and I can't get into degrees of freedom right now. It's usually it's a number of measurements minus one. In this particular case, actually, it's not greater than 30. It's 30. It's the degrees of freedom would be 29 for the type A, but the coverage factor, is 90. For a 95% confidence level, is for this particular case would be 2. Because the degrees of freedom assigned to all type B's is infinity. So you're pretty safe to use a coverage factor of K equal 2. And you can look these things up on the student T tables that I've actually, if you want this, I've added it as extra slides to the end, but if you want this presentation, you're welcome to ask for it. So in this particular case, then we expand the standard uncertainty so we get to that 95% confidence level, because if we only use the standard uncertainty, and those of you remember from statistics, hopefully, that one standard deviation only really gives you a 68% coverage, but we want more confidence that our results, if we put quote our result plus minus the uncertainty and give the uncertainty at a 95% confidence level, then you could say that you're 95 confident that the true value of your result lies somewhere between here, between 0.089964 amps plus minus 0.0035 amps. So that is your final result. And like you said, I rounded to significant figures, according to the GUM and recommendation of the GUM and requirement of P14. So, uh, just to summarize, and I'm just going to go through this really quickly. We these are the 10 steps that you can follow step by step. So it's really, the GUM is very much a recipe book. It's not easy, the hardest part of getting your uncertainties right is not following this recipe, but is really to determine uh, what your uncertainty contributors are. Because if you don't know your measurement system, if you don't know your process really well, and you are completely blind to certain significant uncertainty contributors, then your uncertainty is gonna be much lower than it actually should be. But if you once you know and you have experience in get finding the right contributors, then it's just really like a cookbook here, and you can follow these steps to get started. Um, and here, as promised, and you probably can't read that, but I will certainly be more than happy to send you this. It's just a lot of, you have the GUM, you have the VIM. There are a lot of really, really good publications out there that, and I just really use some of my favorites. Everybody has their own guides that help them understand the GUM better. But you're not alone. There are lots of resources out there to investigate this further. Um, and I think with that, we're at the end, and I don't know what time it is. We have, um, I went over a little bit,
Four
but
minutes.
yeah, right.
We're
So that's
doing
pretty good, considering the material I had to cover. Those of you who are willing to stay, can we stay a little bit longer and answer some questions,
Yeah, I'm gonna
Laura?
go
Or?
ahead and ask a couple of questions. If you guys have the availability to hang on for a few minutes, please do so. This first one says, and this may have already been answered in the meantime, so just bear with me here. Many Cal labs report MU in the same unit as the measured, while other report it in the percent. Which one is recommended?
Both are allowed. So personally, as an end user of a calibration, it depends what it is. Sometimes um, if in resistance, for example, I come from the electrical world. Resistors are very often specified in terms of parts per million, um, accurate drift and parts per or percentage. And so if I see the measurement uncertainty given in ppm, I can compare it to like the drift and see whether this makes sense. I can compare it to the spec. On the other hand, if I have a hard specification listed there on the on my certificate, in and the upper limit and the lower limit is given in in the same units as the measurand, then I would like to see my uncertainties also given in those units, so I can verify that they really fall, that when I take the measurement rand and it falls inside, if I were to add the uncertainties on either side, is it overlapping with the specs, so I can get a good picture, but either way is acceptable.
All right. I've got another question here. One NABL lab can test how many? Question mark.
Say that again.
One NABL lab can test how many? Not sure what it refers to.
I think that may go to our earlier conversation as to how many repetitions is enough. And like I said, it really depends because it depends on the time involved, but it also when we talked about the standard deviation of the mean, it shows that the more you divide by a square root of the number of measurements. So the more measurements you take, the smaller your uncertainty will get. And the better your mean value, the better your measurement result. But it takes time, and time is money. So you really have to weigh um, the need for do you actually get the overall uncertainty, will it really make a dent in the overall uncertainty if you take 30 measurements compared to 5. If it doesn't, is it time well spent? So you have to, there is no good answer. You have to look at it from a case by case situation. But really, that's why the gum says that in some cases, when set each measurement takes a day or a long time, it might be better to set up an experiment and get a typical uncertainty based on that measurement process, get a typical repeatability, and then you might and apply that repeatability rather than from 30 measurements, say, rather than get a repeatability from 3 and have and though in those three representations may not be representative really of the true repeatability. So um, that would be my answer to that.
All right, Helga, it is 10 after, so I'm going to go ahead and cut questions here. I know that people have still continued to type things, but a lot of your questions are really specific. So I've posted Helga's email several times in the chat box. It's halexander@iasonline.org. So you are welcome to reach out to Helga. And I have also posted all of those reference links in the chat box as well, so you can go ahead and copy them directly from the chat box. You might just have to scroll up a little bit because there's been some chatter since then. But thank you again for joining us all and for hanging on, and we really appreciate your time today.
All right. Well, thank you everybody for staying with me. I know it's a bit of a dry subject, but there is really no way around it. Measurement uncertainty is very, very important, and you can't really do it without a little bit of math. So thank you.
Thank you, Helga. Take care.
Okay, thanks. Bye-bye.
Bye-bye. I'll go ahead and leave the screen up just for a few minutes if you guys want to go scroll back through the chat box and copy anything. You're also welcome to email me as well, and I'll just put my email in the chat box here.
All right. Thank you, everybody.
Thanks.